Hey everyone, and welcome back. This is NewportBlakeCTF 2023, hosted by Newport and Blake High School. Overall, very fun CTF. I had a lot of fun. It's also one of those fun CTFs where you're reminded that there's high school students smarter than you. All the challenges I'll be covering should be timestamped in the description. Yeah, let's get started. The first challenge is Algo Gym by Noel Ah. It says, bro, Crute ignored the time memory input-output section of the PDF for given a netcat port and a download PDF. I'm not going to cover the challenge in too much detail, but basically we're given this binary string and we need to step through the binary string to reach from the start to the end. We have a step size, so for this one it's a step size of 3, and we need to determine how many steps it takes to get to the end. So for step size of 3, 0 means you're allowed to step there, and 1 means you're not allowed to step there. So for this first one, if you can step size of 3, we're right here, so we're going to go 1, 2, 3. There's a 1 here, so we're not allowed to step here. We're not allowed to step here, but we are allowed to step here. So for our first step, we could take a step of size 1. And then for this one, we're going to try to step as far as possible. So we can step 3 and we can see 1, 2, 3. So we're able to step here on the 0. And the next time we take as big of a step as possible, we try to step here. We can't, so we step here instead. And then we try to step 3 again and we step here and we're at the end. And so in total, this took 4 steps. That was pretty much the challenge. As I was explaining how to solve it, you probably saw that I kind of already gave the solution. You're supposed to count how many steps you can take, and thankfully you can do a greedy algorithm for this one. So for greedy algorithms, it basically means just like try to do the best, and if you can't do the best, just kind of subtract a little until it is the best solution, and you don't have to really worry about anything else. Just like always going for the best will get you into the correct spot. So anyways, that was the solution. We're just going to do a greedy algorithm. And like I said, there's a little bit more to the challenge, but that's basically the idea. There's going to be different staircases and different test cases, and you need just output. And if it's not possible, you give a -1. I'm not going to cover the code in too much depth, just a couple little tips, I guess. I use Pwn tools for both local and remote. To get it to work locally, I just catted out the input file like this. And so that way you can still do like p.receive-line, and it should kind of match what you do on the remote side. The only difference is you can't do a p.send-line on the cat. But not a big deal. So that way, like when you're ready to test remotely, you can just connect to the remote host. Otherwise, everything's pretty standard. We're going to input the number of test cases just using p.receive-line, grab that integer, grab in all the input variables. There were some issues with the challenge for a while where it wasn't starting with zeros. This is just to fix that real quick. Make sure that we have all the data we need. And then other than that, like I said, we're just going to go through and we're going to try to take the maximum possible step we can. So for that test case, it was 3. So some other ones, might be 5 or 100 or whatever. If we can't take the maximum one, then we're going to try, instead of a 3, we're going to try a 2. And then if we can't do a 2, we're going to try a 1. And if we can't do a 1, well, then we're not able to solve it and we return a -1. That was pretty much it. I'll let it run in the back. And we get the flag. It says, MBCTF, why are you so greedy? So fun. The next challenge is Algorithm Sudoku, also by Noel Ah. It says, let's play Sudoku. We're given a netcat port and a download Python file. In the Python file, this is the server file or the challenge file that's running. Basically what's going to happen is it's going to create a large Sudoku board and send it to us, and our goal is to solve the Sudoku board. This is a pretty tricky challenge to solve it normally. Sudoku, even once the boards get larger, it's very expensive computationally to solve them. So I'm guessing there's some sort of trick because the way they generate boards is they only give us 1 number for each row. And so I'm guessing, yeah, there must be some trick for solving it. I tried doing the standard solution where you do that, like you go through the states and you just brute force it. And as soon as you hit a place that you're not able to put in a valid number, you go backwards through your states and you update it. And so, you just have your brute force sort of depth first search, I guess. But it was too slow. So I looked at the submission code a little bit longer and I realized that they're missing a validation step. And so you can cheese the solution. So I did that and I thought that was the solution, but then another Sudoku challenge was released, the Sudoku's Revenge. So somehow this is solvable. I don't know how, but I will be talking about the cheese solution, which you can use for the first one. And the cheese solution works. Like I said, we have to submit a valid Sudoku board, and how they do their validation for the Sudoku board is they check, let's imagine we had a 9 Sudoku board, like 9 Sudoku board, like the standard Sudoku board. Every row and column must have, all unique numbers from 1 to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this board checks, it takes each row and column, and it just adds up all the unique numbers in that row and column, and it makes sure it's equal to the width of the board. And if it is, you win. The problem with the validation code is it doesn't check that the numbers are inclusive of 1 and 9. So you can output numbers greater than 9 or less than 1. And since if you do that correctly, all the numbers will be unique. So you don't actually have to solve the board. You're just going to put in a bunch of numbers. So if the board was 100 by 100, for every empty square, you're just going to put in 101, 102, 103. And so the unique numbers in each row and column will also always be equal to the length of the board, and you win. So that was the cheese solution. Wasn't too much to it. The code's pretty ugly because I copied it from my real solution. This is the real solution I was working on. Like I said, it's doing that back-ticking iterative sort of process. Just way too slow. So I'm guessing there's a real solution out there somewhere. There must be because there was a revenge challenge. But basically, you're just going to go through. You're going to load in the board. They're going to tell you how the board is constructed. And then from there, you're just going to go through every space that hasn't been filled in. And you're just going to auto-increment and add a new number. And then you send that back to the server, and you win. So we can run it real quick. Python 3, cheese. And there we go. We get the flag. NBCTF constructives. So fun cheese. The first crypto challenge is Caesar Salad by Super Beetle Gamer. It says, every CTF needs an introductory crypto. I found a Roman emperor that made a super cool cipher. Can you decrypt this one for me? We're given a output.txt. If you open up the output.txt, just ciphertext, we can see we have a Caesar cipher. So you just take this to CyberChef. We say we want a ROT13, which is a Caesar cipher. We give it the input, and then you can just cycle through until you find the one that is the correct flag. We know it starts with an N, so you just go from whatever it was all the way up to N, and you get the flag. So NBCTF, hope this wasn't too hard of a start. The next challenge is Crypto 32 plus 32 equals 64 by Null Ah. It says 64 is too much, but 32 isn't. 32 plus 32 is equal to 64, and we're given 2 download files. So if we look at the download files, we're given just a big chunk that looks like this. This kind of looks like base 64, so the first thing, especially with that equal sign at the very end, so you can base 64 decode it, and when you base 64 decode it, it still looks like base 64. So I think the challenge was just keep base 64 decoding it, and eventually you get something. So I wrote a little solve script to do that. We're just going to import base 64. We're going to open one of the files. So first I started with the first file, while true, base 64. Eventually it's going to error out, but by then it should have already printed out something exciting. So we'll do Python 3, solve. And you can see it's just doing base 64, and as every time you base 64 to code, it gets smaller and smaller and smaller. And at the very last, it says NBCTF, hope. Then it errors out, but we don't really care. We got the first part of the flag, which I put there. And then we can do the second file, same sort of thing. And we get the rest of the flag. Hope you had fun. So interesting. The next challenge is Crypto Rivest-Shamir-Forgot-Adleman. By Super Beetle Gamer. It says, exponents took too long. I decided to use an alternative. It won't about the same, right? And we're given an output.txt and a child.py. So for this one, it's RSA. They're generating 2 primes, they're calculating n, using some very large E, which is strange. And then we have the flag and a message. And then they're doing CT, M. In other languages, this looks like it would be to the power, so M to the power of E. But this is XOR in Python. Which they also hinted. Otherwise, it would look like this. So we have M XOR E mod N, and then they give us the output. This doesn't make any sense. This is not RSA or anything. Since M and E are way less than N, if we look at the output file, the ciphertext and E are way less than N. Basically, we can ignore this mod N. And so basically, we have CT and E, and we need to calculate M. And XOR is reversible, so we're just going to take the XOR of CT and E, and we should get M. So that's what the solve script looks like. I just copy out all the values. We don't even need this. And we do plain text is equal to the XOR of CT and E, and we print it out. So let's do Python 3, solve. Python 3, solve, and there we go. NBCTF, who told me to use XORs? This is Crypto SBG-ABW's Insanity by Super Beetle Gamer. It's a skill issue by Anonymous Blue Whale, and we're given 2 download files. For this challenge, it's kind of an RSA challenge, but instead of determining the plaintext or the ciphertext or something, we have to determine the modulus, which is not given to us. Normally the modulus is, the N, which is usually public, but in this challenge, it's not. What's also strange is it's going to calculate 2 different ciphertexts using 2 different moduluses, and somehow using that, we're going to determine one of the factors for the modulus. So pretty interesting challenge. To solve it, we just need a little bit of math. So like I said, actually, let me just go through the code. So we're given a message. It generates 3 primes. From there, it's going to generate an N1 and an N2. And we can see it's going to use a shared factor, this p, on both of those ends. There's an e. It's going to generate the ciphertext using RSA for both of those, using the same message, the same e, but two different moduluses. Then from there, it's going to take one of the primes, Q1, and generate an AES key and encrypt the flag. So our goal is to find Q1, which is one of the primes. So like I said, to do this, we just need a little bit of math. If we step out here, so these are the values. This is what's happening. If we write this out, so it is E mod N1, and CT2 is equal to M to the E mod N2. So basically, we're going to rearrange this equation so that we can do a GCD. And I'll talk about that in a second. But basically, so we have these two equations. This equation is the same as CT1 is equal to M to the E plus some constant times N1. So we got rid of the modulus. Instead, we did plus, and we introduced a new variable. We don't know how many N1s were used, but some amount of N1s were used. And we're going to call that value A. We can rearrange this equation. We can bring this to the other side. So we'll bring it to the other side, and now we have this. We know all the values on the left. We know CT1 and we know M to the E. We just don't know this value. So we can do that the same thing for the second equation is equal to B times N2. And so now we have this equation and this equation. N1 is equal to P times Q1 and N2 is equal to P times Q2. So we can see that this value and this value both share a common P. So if we were to take the GCD of these two things, GCD A times P times Q1 and B times P times Q2, it'll be equal to the common factor, which is P. So we can calculate this, take the GCD, and we have P. So now we have P. Our goal is to calculate Q1. So let me take this down. Now that we know what P is, we can divide this side by that side. So let me dial it. Divide by P. So we can calculate this value. So this is just, some constant. Thankfully, I don't know if this is the intended solution, but this was factorable. So Q1 is a large prime, but A doesn't have any guarantees to be prime or anything. And thankfully, it's somewhat smooth. It has a bunch of little factors. And so we can just factor all of those things off. So I used a combination of factor DV and sage factor. And eventually I was able to calculate what A is just from all those factors. And you're left with a large prime that's thankfully 196 bits in length. And that's Q1. And once you have Q1, you just do the rest of the AES, you generate a key, and then you can decrypt the flag. And that was it. So this is what the solution looks like. We take the two ciphertexts. Like I said, we were given a bunch of values. This is the values, ciphertext 1, ciphertext 2, and encoded flag or encrypted flag. We copy those out. We take our message, we calculate that value, and then like I said, we're going to do the GCD. So we're going to do the value minus ciphertext 1, value minus ciphertext 2. We calculate P. From there, we calculate AQ1 and AQ2. This is A. Sorry, actually, this should be a B. BQ2. We don't really need it, though. I was just printing it out. And then from there, we're going to take those values. Like I said, I took AQ1, which is A times Q1, and we need to factor out A. I took it to factor DB, it got some of the factors, and then I'd use sage factor and it got the rest. We can see here's a factor, and then here's some big factor. And thankfully this factor was 1,000 whatever bits long. So we know it's probably the correct Q1. And then from there, we just do the reverse AES encryption, the decryption. So we take the hash of Q1, we pass it into AES, we do decrypt, and we get the flag. So Python 3, solve. And we get NBCTF, congrats on finishing the 3-parter. So, fun. The first misc challenge is misc, do you hear that? By Croot. It says, I'm not sure why, but when I look at this image, I can hear some sort of faint sound. Do you hear it too? So if we download the PNG, we're given this. I think this is Flocto's profile picture. So we can take it to a Perry solve. So we select an image. We give it help.png. We submit. And if we go through, eventually we'll see that zstag detected some WAV file. So there's some embedded WAV file in this image. So we can run zstag on it. So you go zstag and then help.png. We can see it did find it. And so we need to extract this. So we do zstag help to look for the command. It's -e. So we're going to extract it. And we give it the file. Oops. And so we're going to say out.rif, cool. From there, let's just open up the new one, out.riff. We're given this, this file is, this program is called Audacity. If you listen to it, it's just like a bunch of beeps and stuff. It doesn't make any sense. So we'll load it in Audacity, and we go to spectrogram, and we get the flag. It says, NBCTF, you have some good ears. The next challenge is misc not accepted by null aw. It says, I can't seem to pass this problem. Can you help me? And we're given a code forces link. So if you go to this, you can read the challenge. Basically, it says calculate the sum, but 2 plus 2 equals 5 or something. So definitely a misc challenge. So if you just try submitting different things, so I submitted a print 5, and when you do that, the checker log says flag part 1 of 3 NBCTF. Nice. So we're going to be submitting some different types of input, and I guess the checker is going to give us different parts of the flag. So first I had it just print out 5. The next time I had it print out something wrong, so it printed out 4, and it said just print 4. You can see my Python script here, and I get the second part of the flag, and it says you got all, and then I tried a timeout. It wasn't that one, and then I submitted, I think, a string, the wrong type, and I finally got the last part of the flag, and it says all my verdicts. So fun. The next challenge is osint persona by right-click. It says, I have this username. Can you help me uncover who it really is? They go by the name intowin9945 online. So we can look for a username checker, username searcher. I forget which one I used. Maybe this one. And so we're looking for intowin9945. Eventually, we see its Twitter is taken. So we can just go to this one. We see intowin9945, I like to type. We can see they're using monkey type, and those are their only 2 tweets. So cool. Let's check out monkey type. Monkey type. We go here. It is a typing test apparently. So we're going to look for their profile. If we go to the Hall of Fame and just click on someone, we can see the profile URL looks like this. So let's use theirs. Type in V into win, and cool. We can see they have 2 social medias. They have the Twitter, which we already saw, and they have some blogspot. So we can go to a blogspot. Let's see. It says, really trying to type fast, practice, typing in burst, maximum speed, can't break 200. Let's visit their profile. It looks like they have a Casper's Bring Dump, and they're from Norway. All right. So let's go to this. Trying to host a new blog. I use this to post actual CS related things. Here's an image. Cool. Just found out he loves to self-host. Cool. We go here. I'm trying to find a job. I heard from my LinkedIn friends it's a good place to people. Blah, blah, blah. Edit. Sorry, I had to delete the image. I realized it contains some private information. So apparently there was an image on this blog, but it's no longer there. So we know what that means. We go to Wayback Machine. Wayback Machine. So let's see if the image was saved. It looks like the image was saved at some point. So we go to the 30th, and let's load this. Nothing there. We're looking for the LinkedIn post. Oh, and there's the LinkedIn post. So we now know what their LinkedIn is. So let's check that out. Casper Mellingen. Melling. Cool. Oh, well, we just saw the flag actually. So here's the user, and here is the flag. So it was one of their posts. It says NBCTF, oops, you found me. So pretty fun osint challenge. Normally I don't like them, but I feel like that one was fun, very logical. The next challenge is osint linked out 1 by goodbye. It says, I just finished setting up Newport Blake's LinkedIn. I hope I didn't give away too much personal information in my profile. Someone might even be able to find a flag hidden in there. Cool. If I search for this on LinkedIn, it didn't pop up. And if I search for it on Google, it didn't pop up. But if I use DuckDuckGo, for some reason, it worked. So we'll go to here, LinkedIn. Newport Blake on LinkedIn. Looks good to me. Cool. So we have some user. This looks correct. Forget where the flag was. Oh, here we go. Flag designer for NewportBlakeCTF, in charge of designing flags, blah, blah, blah. There's some imager, so let's follow that. It says fake flag, but we're given some hex. So let's go to CyberChef. From hex. we're given another imager. Go to that. And if we scroll down, we get the flag. NBCTF, did I make a good flag? The first challenge is pwn ribbit by Crute. It says, oh no, my pet frog got stuck inside a giant hole. Can you help him rop out? We're given a netcat port and a couple of download files. So we're given a C file, which is much appreciated. In the C file, there's 3 functions. We're given a main function. The main function is going to set some buffering and then call frog. Frog is going to have a buffer overflow. It's defining a 25-byte buffer, but then we call an unbounded gets on it. So we can definitely buffer overflow, and it's a ROP challenge, so this is probably where we're going to be cropping from. And then we can see we have a win function. The win function wants a jump height and a care motivation. It's going to load and read the flag, and then it's going to check those input parameters. If the jump height is equal to flocto beef and string compare of motivation is equal to you got this, and the string compare of just do it motivation plus 21, then we print out the flag. So we need to call this function with these arguments set correctly. The one trickiness to this challenge is there's no string in the binary that exists that has this string where it says you got this, and then at offset 21 is just do it. These strings do exist in the binary, but not in that format. So we need to construct this string somehow. So like I guess the first most obvious way would be to like put it on the stack. So when we're doing this buffer overflow, we'll also put these on the stack. The trickiness is then you need a stack leak. It's not impossible. I'm sure it's doable, but it's just a lot of work. An easier way is while ropping. While you're ropping, there's plenty of gadgets in here. I think libc was included. So we can do a rop call to read, and we'll just put in a node address. I'm pretty sure there was no pi. Make Ubuntu 22. Let's check sec. It was called ribbit or something. Yeah, there's no pi, so we can find the address of some writable section like the BSS, and then we're just going to rop to a read call and just read in a string to this address, and then we'll use that address as our motivation string. And so that way, yeah, we just construct the string manually and we don't have to deal with leaks or anything like that. And yeah, that was the challenge. So if we go to the solve, I'm just going to cover this stuff once. So we're using pwn tools. I disable warnings. I shouldn't, but I do. We're going to set up a bunch of context. We load in the elf. I set debug so we can see the messages passed back and forth over the socket. I use tmux, so I do some terminal splitting here. We're going to load everything up. So we need to find a writable section so we can do that read call. I just use the BSS. You can use anywhere that's readable. Sometimes you might clobber something, so you do need to be careful about using that. We're going to construct our ROP payload. Pwn tools does this for us. It's absolutely amazing. So it's going to find all the pop register calls for us to call these functions. And basically, we're going to say ROP first to a read in from standard in to the buffer address. So this BSS address, I think it's like 4,500 or something like that, or 45,000, and read in OX 100 bytes. And then once you're done with that, jump to ROP.win and pass in this value and our buffer, and that's it. So we're going to do that. We're going to send in 40 bytes. You can calculate this by doing a pwn cyclic or just figuring out when it actually starts. If you look at it in Ghidra, let me go back. This is the code in Ghidra. You can see it's going to define a 32 byte buffer, because I think in the C code it was 25 bytes. Yeah, 25. But when it needs to be machine aligned, so it's going to be 32 bytes. And then you're also going to have your RBP on the stack, so it's going to be 40 bytes. But you can also use a pwn cyclic to find that out. But we send in our 40 bytes, so we fill up the buffer, and then we can start ropping. And then after that, once it starts ropping, it's going to do that read call. So we're going to send it the string we want, p.send, you got this, and then add an offset of 21 or whatever. It's just do it. And then from there, it should print out the flag. So Python 3, solve.py, and we get it. It says NBCTF, you're welcome, Quasar. So fun. The next challenge is pwn heapnotes by Crute. It says, don't know heap exploitation, read this. We're given a netcat port and a couple of download files. I like this challenge. It's very beginner friendly. It is definitely a beginner heap challenge, which is good. So if you've never done a heap challenge, I'd highly recommend trying this one. There's many different ways you could exploit this binary, and it's really not too bad. So it's a standard note-taking sort of application. You have your CRUD operations, create, read, update, delete, and there's pretty much no checks done anywhere. So for creating a note, it mallocs OX 40 bytes, and you can give it some data, which is nice and simple. Then for read, you can read a note. You just give it an index. It makes sure that you don't go past the number of notes you've created, but it doesn't check to see if the note was already freed, meaning you could use it to leak an address. You can update a note, so you pass it an index and you can put in new content. Again, it doesn't check to see if a note was already freed, which is what we're going to be using to run the exploit. And then there's delete note. You give it an index and it will delete the note at a location. And again, it doesn't check to see if it was already previously freed, so you could do a double free. So we have a lot of different exploitation gadgets here, but we're just going to keep it simple. For this binary, their pi was disabled, so we know where the address of everything is, so we don't really need a leak. There's also a global offset table. If you're not familiar with the global offset table, basically it's just like a jump table. So when you use other libraries, those libraries could be random, anywhere random in memory, and the global offset table, along with something called the PLT, is just a mechanism to kind of find those like remote addresses within your process. But what you can do is there's this global offset table. You can overwrite values in the offset table so that when a function is called, it'll look up that address in the table and it'll call that. One of the addresses in the table is the exit function. So this will call out to, you can kind of see it says call to this external exit function. So the binary doesn't know where this function exists yet. So when you call exit, it's going to jump to that global offset table. It's going to look at that address and then it's going to jump to that address. We're going to overwrite the exit with a win function. So somewhere in here, there's a win function. Here it is, win. And the win function is going to call system bin shell, sorry. So we know what our target is. Like I said, we're just going to overwrite the global offset table entry for exit with the win function. To do that, there's a bunch of different heap exploitation techniques we could use. The one we're going to be doing is we're going to create two notes, and then we're going to free both of those notes. And when you free them, the heap has these things called bins so that they can reuse previously allocated chunks. And what we're going to do, and the bins are connected, they reuse the heap chunks and they put pointers in those freed heap chunks. And so it's like a linked list of pointed chunks. So what we're going to do is we're going to overwrite one of those pointers such that instead of pointing to the next chunk, it's actually going to point to the global offset table entry for exit. So then when we start creating new chunks, it's going to follow that linked list. And at some point, it's going to create a chunk that exists within the global offset table instead of being in the heap. And once we have a chunk in the global offset table, we can write contents there, and we're going to overwrite, like I said, that global offset table entry for exit with the entry or with the win function. And so when we call exit, instead of exiting, it's just going to call win, and we get shell. To see what the solution looks like, really not too bad. So we're using standard pwn tool stuff. Here are the different functions: create, read, update, delete. So like I said, we're going to create two different notes, A and B. Then we're going to delete those two notes. So they should be in the free bins. We're going to do a GDB attached just so we can inspect, and I can show you some GDB tools. This is your first pwn challenge. Then we're going to update one of the notes, update note 1, and we're going to give it the address of the global offset table. So this is a freed note. And right now the contents of that freed note or that freed chunk is just a pointer to the next chunk. But we're going to overwrite that pointer instead with a pointer to the global offset table. Then we're going to create a note. This is going to create a note like a standard heap chunk because there's multiple things on the heap. But then the next chunk we create will actually be the chunk within the global offset table. And when we create that chunk, we're just going to give it the address of win. And then we enter in an interactive. So for debugging and running these challenges, there's a couple useful tools. Hopefully this is large enough, but if I make it too much smaller, it just doesn't look good. So one of the tools is viz heap chunks. So let me push this up because I think my face is covering it. So we are at the point where we have created a chunk A and created a chunk B, and then we deleted the chunk A and chunk B. And so if we look on the heap, we can see we use the command viz heap chunks. We can see there's the tcache bins, and it's saying there's two entries on the tcache bin. We have this one and this one. So originally I had 24 A's, so it would have been all A's, A's, and A's, and all B's, B's, and B's. But like I said, it's a linked list, and we can see this is a pointing. This address here, 11042A0, is this address. So this chunk is pointing to this address. Cool. So instead of, and that means that when these are, when we create new chunks of the same size, it's going to use these, and it's just going to follow this linked list of chunks. So if we had more chunks, they would all just kind of point in a row. But since we can edit chunks, we're going to edit this chunk and instead put in the address of the global offset table entry. So you can type in global offset table entry. Let me push that up. These are our entries in the global offset table. So at this address, this is the address for this memory address contains the address to free. So free is a libc function. By default, the binary doesn't really know where this function exists until it's loaded. And so once it was loaded, it was determined it was at this address. So this address contains this address. And so you can kind of examine it. So if we wanted to examine the hex at that value, So let me push that up. If we examine an address at this, we can see we get free, which is this address right here. So cool. Like I said, we're going to overwrite exit. Right now, exit hasn't been resolved yet, so this is pointing to some resolver code. We're going to instead change it. Instead of jumping to this resolver code, we're going to have it jump to win. So we can print out the address of win. Let me push that up. Print win is right here. Cool. So another useful command is bins. Right now, the bins on the heap are fine, so it's pointing from this chunk to this chunk. But if we jump through, so I put a break statement in the main function, so every loop is just going to break again. So if we look at the heap chunks now, this was pointing. Let me move this up. This heap chunk was pointing to this chunk, but now it's pointing to 404068. If we look at the global offset table, that's this. So right now it is now, instead of, we did an update call, and instead of pointing to the next chunk, it's pointing to this address. So if we create a chunk, let's look at the bins. We created and allocated the first chunk, and so now libc thinks it's following those forward pointers. Libc thinks that the next valid heap chunk is this address, the global offset table. Obviously, this doesn't make any sense, but it's good for us as an attacker. So when we create our next chunk, so we do step, then we look at the bins. We can see that chunk was created, and if we look at the global offset table now, we can see that the exit is now contains the function win. Cool. So if we were to call exit now, instead of jumping to the resolving code, it is now going to jump to the win function. So we hit continue. We go over here and we're going to press exit. And cool. We say ls. Oh, we're in GDB, so it's going to be all confused and everything. But basically, we have shell now. So that was it. Really not too bad of a challenge. So we can run it on remote. Let's make sure we get rid of GDB. Python 3 solve. It's doing everything. We exit out to call shell, and there we go. We have shell. It says NBCTF, baby's first heap. So fun. The next challenge is pwn ret to thumb by unvariant. It says I can't figure out the difference between ARM and thumb. We're given a netcat port and a download file. So starting out, I'm not that good at ARM, so if I mess something up, I apologize. I just kind of stumbled through these challenges. This challenge in particular took me way longer than I would like to admit, but eventually I got there. The difference between ARM and thumb, again, this is not my specialty at all, but I think ARM is like 32-bit instructions and thumb are like 16-bit instructions, and you can switch between ARM and thumb mode. So I think that's what the difference is, and maybe that's what the challenge was like recognizing this blob of code, which doesn't automatically disassemble, but we'll get back to that in a second. Anyways, so there's a main function. Like I said, we're given an ARM binary. You can open it up in Ghidra. ARM syntax is obviously different. It's a different architecture than the normal sort of Intel AMD syntax we're used to. There's a different calling convention. But other than that, it really isn't too different. Like, instead of a return, we don't have that, but instead it's just going to pop things off the stack. Like I said, there is a different calling convention, which kind of comes into play when you're doing ROPs and stuff, but it's not as different as I thought it was at first. But anyways, so we have this vulnerable function. We go into this. We can see it's defining a 32-byte character buffer on the stack. It's going to say, can you ret to thumb? And it's going to then do an unbounded get, so we have a buffer overflow. So ret to thumb is probably like a play on ret to win. We need to jump to a win function. What was confusing me for the longest time was there was no win function. Like if you look at this, like you can go through all the functions and there just isn't anything. And so I thought we were supposed to, like return to libc, and I was trying to get like a libc leak, and it kind of worked, but the code was just so messy and there's just not that many gadgets. Eventually you kind of play through, and it's strange that they give us this bin shell string, which makes you think that maybe it isn't a libc, because if you have libc, like there's already bin shell, like you wouldn't need this extra string, but there's no system call in here. So I didn't know if it was just like some random ARM crap that maybe you can call to libc, or libc is at a known location or something. I didn't know. And like I saw these weird bytes and I hit disassemble on it, and you get these like weird instructions like this that, I think it's just garbage. Like who knows what ARM's doing? Like it turns out that maybe because it was called the difference between ARM and thumb, instead of just doing a generic disassemble on these random bytes, what you can do is a disassemble ARM. And if you do a disassemble ARM, you'll see that it's going to load this string into this register, load the string to this register. This is the calling convention from R0. These are the registers for ARM. So R0 to R4 is how you push variables to call. Then it's going to move OXB into R7. This is the calling convention for making syscalls. And specifically, OXB 11 is execve. So this is basically shell code for spawning shell. We just had to know this code existed here. And so this is the win function. It just doesn't decompile. by default. These then get, it's loading 10570, this code into R0, or the address of this. This got decompiled, this was our bin shell, so you can just do clear. We'll do C, C, C. So the whole challenge was realizing that the shell code already exists within the binary, you just had to find it. Gadget by default didn't decompile it because it's thumb code, I guess. But yeah, so all you have to do for this challenge is just jump to this address and it will spawn a shell. So if we look at the vuln function, like I said, we had a buffer overflow, it's unbounded, 32 bytes. If we look at the return signature, I'm not sure if this is correct. This might be another ARM versus thumb thing, but basically it's going to pop the PC, which is like our RIP, off the stack. So when we do our buffer overflow, very similar to how we pop RIP off the stack, it's also going to pop PC off the stack. And so if we just put the win function on the correct spot on the stack, it'll pop this, and we get the shellcode to run. One of the tricky things is like getting a setup that works. I found out that this is a setup that kind of works for me. And so what I do is I do p is equal to pwn process run.shell. If we look at run.shell, this is it. By default, we were given code that looks like this. But if you put this in here, this will start the debugger on port 12345, and it'll wait for the debugger. So we wait for the debugger, and then we do a gdb attach p. This doesn't work. It doesn't just attach to it, but you just kind of ignore it. Really, we're just spawning a debugger, and then we're going to set the target to connect to the QEMU process, and then we set a breakpoint. But anyways, this kind of worked pretty well for me. And so if we run it, Python, or let me join tmux, python 3, solve.py. We can see, we have a debugger, and it's our standard sort of setup, even though it's running in QEMU. Anyways, if we hit continue, eventually we're going to jump into this vulnerable function you can see on the left. And if we single step, it's going into puts. So let's finish puts. We can see we got can you write to thumb. Then we're sending our payload. So let's take a look at the payload we're using. We're just going to fill up the buffer with a bunch of A's, and then we're sending the address of that shellcode. So one thing that's strange, another difference I'm guessing between ARM and thumb, again, this is not my specialty, is the address of the shellcode was at 10560, but that doesn't work. For some reason, if you put in a +1, it does work. And I saw this when I was running some ROP code, it would also offset. I don't know why, but yeah, if you offset by 1, it works. I'm guessing that's how it enters thumb mode. Don't really know. But anyways, if you continue, eventually it's going to do that gets. Right now, it's going to return from vuln to main. But if we finish this call, it still says it's going to return to the main. But if we keep going, oh, finish gets, we can see it's going to return to 10.0560. Interesting. So we do a single step. It moves R0 to R0. Then we're going to subtract 4 from the stack. And then it's going to subtract FP, or it's going to pop both the frame pointer and the program counter from the stack. So we do that single instruction, and then at that point it jumps into our shellcode. So this was the shellcode that we saw earlier. SVC is like how you do syscalls. So we do single, so it loaded bin shell into R0, and then it loaded, I don't know, some other values. And eventually it should jump into shell. So we'll just hit continue. And it says it's closed. We jumped into an exec VE. We just go over here, we can see we have shell. So cool. Really not too bad of a challenge. We just had to return to a single function. If we run it on remote, Python 3, solve. And we have shell. So we can cat out the flag. And it says NBCTF ARM is fun. So really not too bad of a challenge. It was just tricky to find the shellcode in the process. The next challenge is pwn canary-in-a-coal-mine by Unvariant. It says golden canary sings amidst the darkened coal, warning whispers death by ChatGPT. Pretty nice poem. We're given a netcat port and a download file. Thankfully, we're given a C file. There's a menu printer, some code that grabs a number. It's going to define some minecarts, 8 of them, a bunch of variables. Then we're going to enter in a while loop. And so we have a bunch of different options. So the options where we can mine, extract, collapse, and abandon. So for mining, it's going to ask us for a position and a depth, and then it's going to kind of recursively grab whatever is at that address, but kind of telescoping through. Then we can save the coal, whatever value we mined, onto one of our minecarts. We can collapse a minecart, so it's going to do a unbounded gets, which I guess is kind of like a buffer overflow. And then we can print goodbye, go to done, and it'll return. And then there's also a win function. I think my solution for this was a little bit cheesy. I think it works. I mean, it's basically the same. I think the idea was that you were supposed to leak the canary or something. But what you can do instead is, I guess there's two different bugs. First off, the minecart index is unbounded. And so if we look at minecarts here, there's only 8, but we can go past it. And the whole thing about this challenge is canaries were enabled. So there is a canary, so we can't just do a buffer overflow and clobber the return address on the stack. Otherwise, we would clobber that canary. But since we can access minecarts and it's unbounded, we could access index like 20, for example. And so this would be 8, 9, 10, 11, 12, 13. Address 14 might be the canary. And so we could then just skip over it, and address 15 would be the return address. So we don't even have to touch the canary, we're just gonna jump over it. The other thing that was strange is here we're able to insert an address, and then it'll kind of telescope, so it'll take the address of that, resolve it, take the address of that, resolve it. But we can do that addressing, or the telescope resolving, 0 times. So we're just gonna pass it a random address. And pi was disabled, so we know where the addresses of things are, so we can just pass it the win function. So what we can do is we can just load in the win function as our coal. We don't have to do any resolving, so we just have the win address is equal to coal, and then we're just gonna save that as the return address. We're just gonna jump right over the canary and everything else. We're just gonna save it, and so then when we say goodbye, we just jump to the win function. Like I said, I think there was more. They give us this buffer overflow, so I think maybe we were supposed to leak the canary value or something like that, but we don't have to do that. And that was pretty much it. So let me jump into Ubuntu. Pretty much everything else was the same as last time, doing some pwn tools. I used the same sort of QEMU setup as last time, where I do this pwn process run.shell, and then I do the target remote for debugging. Yeah, otherwise, like I said, we're just going to save the win address. The win address is at elf symbols win here. So we save it, we're mining for it. And then I just save into a bunch of different places. I forget which one it was, so I just spammed it. And then, yeah, that's pretty much it. At the end, we say we want to exit, and we should just jump straight into a shell. So Python 3, solve.py. Says goodbye, we do ls, and we won. So we can count out the flag. It says MBCTF, imagine storing the canary in the binary. So I'm guessing this was not the intended solution, but still fun. The next challenge is rev crisscross by Flockdo. The description just says X, we're given an output file and a main.py. If we look at main.py, it's just some custom encoding function. There's a couple of keys. It's going to do some swapping into these keys, and then some weird sort of encoding byte by byte. What's going to happen is there's going to be some integer x, and at every step through this encryption function or encoding function, it's going to add a byte to the start and a byte to the end. And these bytes are the n and w, and they're generated from this encryption function. To make things a little bit more complex, every other round, it's going to swap n and w. So we have to know, is it n first or w first? And yeah, as part of the output file, it gives us the 2 keys and the output variable. So yeah, I don't really have anything too insightful to say for this encryption function. Basically, you just kind of reverse it. What I ended up doing for the encryption function was I wrote this decryption function. I know that I need to figure out what value corresponded to the n and w here. So I just iterate through every value and figure out what the correct output is. It's possible this wouldn't work correctly. There could be multiple values, but it ended up working. I'm guessing it should be reversible. Otherwise, this challenge would be very difficult. And there could be like false answers, which I don't think that they would want. For doing the rest of the decryption, like I said, we're given an integer and we need the bytes at the start and the end. What I ended up doing was just converting it to a binary string and just kind of slicing off 8 bits at a time. Probably many ways you could do this. But I slice off the binary. And yeah, so I grab the n, which is the values at the end, and the w's, which are the values at the start. I might have those reversed. I print them out, then I call the decryption. I don't know what the swap order is on them, so I just try both of them. And if I get a valid value out, I just assume it's a part of the flag, and I print it out. And that was pretty much it. So do Python 3 to solve. So like I said, this is that giant binary string. I just chop off like, the first 8 and the last 8 at the end. These are the values, convert those to integers, and then run it into that decryption function. And at the end, you get the flag. NBCTF crisscross strawberry sauce. So, the first web challenge is Web Inspector-Gadget by Goodbye. While snooping around this website, Inspector-Gadget lost part of his flag. Can you help him find it? And we're given a URL. So this is just a flag finder challenge. The flag is split into 4 different parts. So we just need to find all the parts. So we can just go through real quick. You search flag. You'll get the first part, or part 3. You can see it's the alt text for this image. Flag, part 3 of 4, we can see detective. We can also see there's a function here called getFlag. So we can copy that out, Go to that URL. We get part 2 of 4, job. If you go through all of these, eventually one of them, I think it was magnifying glass. Yeah, magnifying glass. The title is also another flag, so we can see flag part. And if you can't see it, you can go to view source, look for title. Flag part MBC to CTF, good. And the last flag was on robots.txt. We go here, it says don't allow scrapers to go here. So if we go to this URL, here's part of the flag for your troubles, part 4 gadget. And that was all 4 parts, put them together. I think it was like go inspector-gadget or something like, or good job inspector-gadget. Yeah, that was the flag. The next web challenge is Web Walter's Crystal Shop by Crew. It says, my buddy Walter is selling some crystals. Check out his shop, given a URL and a download file. Here we can see there's just a little inbox. We can type some stuff, it says no crystals found. Maybe if we do an A, we found some crystals. Cool. So if we open up the source file, there's an app.js. We can see it's reading in a flag file. It's going to create some databases. It's creating two tables. There's a table called crystals, which has 3 values, and a table called flags, which just has 1 value. If we go through, we can see there's this app.getCrystals, and it's going to do a query, and we can see we have a SQL injection here. It's not doing any validation on names, so we can bypass this. And then just pretty much nothing else. So we just need to write a SQL injection. We can do a little union. So right now it's reading from the crystals table, but we can read from the flag table. We just need to make sure that the columns align. So if we want to do an injection, we could use SQL map or something, but this one really isn't too bad. We can just write it ourselves. And SQL map probably isn't allowed for the CTF. So ChatGPT or Copilot tries to do it, but doesn't quite do it correctly. So we're going to close out of this light query. Then we're going to do a union, select, flag. This is grabbing 3 elements, and so we should also return 3 elements. So we're going to grab flag, and then null from flag, and then close out the rest of the query. So we can run this query, search there, and we get something out. It says NBCTF. Hopefully the DEA doesn't know about the other crystals. So, fun. The next challenge is Web Secret Tunnel by Crew. Can you find the flag on the other end of my secret tunnel? We're given a URL and a download file. If we look at the download file, there's 2 different Flash servers running. One of the Flash servers is called flag.py, and there's just a single route which has the flag, and it's running on port 1337. The second one is this is another Flash server, but this has a route called fetch data. And basically it's going to take in a URL, and if it passes the checks, it will get the URL. So we're doing a little SSRF, server-side request forgery, and we're going to try to tunnel the request into the flag server. But we're not allowed to use 127 in the URL, so we can't use 127.0.0.1, but that's okay. We can just use localhost. We can't have periods. I'm not sure why we would want that. We're not allowed to use X because they don't like Twitter, and we're not allowed to use flag because that would be too easy. So to solve this, this is the solve script. We're going to use request, make a post request to fetch data and the URL, and we're going to request localhost 1337. Instead of doing an F, we're just going to URL encode the F with a %66, and that bypasses the check. And yeah, we're not doing a 127, we're using localhost, and there's no X's, so everything should just pass. So let's do Python 3, solve.py, and we did it. NBCTF secret tunnel. The last web challenge is Web Galleria by Flocto. It says put up some fun images for everyone in this amazing image gallery. We're given a URL and a download file. So in the download file, it is a Flask app. There's this route called gallery, and if the flag file exists or the flag parameter exists, it'll check this, or it'll create the file name. It'll check to make sure it's a valid path, and if it is, it'll return the file. I think the bug with this, if you use os path join, if you specify a full path here, it'll just use the full path. So we're going to see what this looks like. So I'm importing OS. I'm using os path join. So if you do os path join root and temp flag.txt, it'll return temp flag.txt. So as long as we specify to the root, it'll just we'll be able to return the flag. And yeah, that was the solution. We can see where the flag exists from the Docker file. It's just at temp flag. And so if we go to that URL, gallery file temp flag, we get the flag. So NBCTF Wonderhoy. So fun. And that was all the challenges I was able to solve. Overall, very fun CTF. It was good to be pushed to do some ARM challenges. I'm not good at them, so thank you Unvariant for those. I thought the osint challenge, the first one, was very fun, kind of jumping through all the social profiles. The web ones were a little bit on the easy side, but still fun to do. Yeah, thanks Newport and Blake for hosting, and I will see you at the next CTF. Cheers.